Have you ever typed a completely wild question into a search bar and just been stunned that it actually got you? It feels like some kind of magic, right? Like it's literally reading your mind. Well, it's not magic, but it is an incredibly powerful machine learning technique called learning to rank. And we're going to break down exactly how it works. Come on, we've all been there. It's late at night, you type in some frantic, half-formed thought, a weird symptom, maybe a movie plot you barely remember. The thing is, search logs are filled with these one-of-a-kind queries that have probably never been typed before in that exact way. And that really is the central mystery, isn't it? I mean, if a search engine can't possibly have a pre-made answer for every single unique thing we ask it, how does it consistently give us something useful? How does it deal with the complete unknown every single second? Well, this gets us right to the heart of the search engine's big dilemma. You've billions of people coming up with new questions every day. Trying to just memorize every possible question and its perfect answer, it's totally impossible. The whole system would just collapse. So the solution had to be way smarter. Instead of memorizing that one specific article as the answer to weird bump on nose, the engine learns a much more general pattern. A pattern like, hey, when the search words are strong match in an article's title, that's a really good sign of relevance for any query. It's about learning the very essence of what makes a result good. And this total shift in thinking is the core of what we call learning to rank, or LTR for short. It's all about teaching a machine the abstract rules of relevance, so it can make smart calls all on its own for questions it's never, ever seen before. You know, back in the day, engineers literally had to tune the search algorithm by hand. They'd sit around a table and say, okay, let's give a title match a weight of, say, 10, and a keyword in the body text a weight of 2. It was incredibly slow, really brittle, and it would just fall apart with new kinds of searches. LTR automates all of that. It learns the best weights from data, creating a system that can actually generalize and handle the unknown. Okay, so how do we actually teach this to a machine? Well, think of it like a recipe. To train a ranking model, you need 2 key ingredients and a pretty clear set of instructions. Our first ingredient is something called a judgment list. This is basically our ground truth, the answer key. It's a huge list built from things like user clicks or actual human evaluators that tells the machine, for this search, this result was good and this one was bad. It's the cheat sheet the model is going to learn from. The second ingredient is features. Now, these are the signals, the measurable things the machine can actually look at. Stuff like, does the search term show up in the title? How new is this document? How many times is the keyword mentioned? These features are the mathematical building blocks for a ranking model. And here's the recipe itself, the game plan, boiled down to 4 main steps. First, you gather all those judgments, the answer key. Second, you define your features and log their values for every single document. Third, and this is the really clever part, you transform the problem. And finally, you train the actual model. Let's really zoom in on that third step, because honestly, this is where the genius comes in. It's a conceptual breakthrough called the pairwise transformation, and it's how you turn a super complex problem into a surprisingly simple one. The big secret here is realizing that relevance is all relative. A search engine doesn't need to know if a document is a perfect 10 out of 10. Nope, it just needs to know that for any given search, document A is better than document B. It's all about the comparison. Let's take an example. For the query Star Wars, a relevant result like Return of the Jedi has a really high title match score. Search nerds call this a BM25 score. Meanwhile, an irrelevant result like Star Trek Into Darkness has a way lower score. That simple difference, just in one feature, is exactly the kind of pattern the model is built to pick up on. So here's the trick. The algorithm doesn't just look at one document at a time. Instead, it creates pairs. For one search, it grabs one known good document and one known bad document and pits them head to head. And it does this over and over for millions and millions of pairs. And what the machine focuses on is the difference in their feature scores. By taking the irrelevant score away from the relevant one, we get this new number, a positive 4.35. This single data point, this feature delta, is an incredibly powerful signal. It tells the model, hey, in this matchup, a higher title score was a good thing. Now, multiply that by millions of pairs, and the machine starts to learn. So here's the crucial transformation. We take every correctly ordered pair, where the good document has better feature scores than the bad one, and we label it +1. Then we do the opposite for any incorrectly ordered pairs. And just like that, our messy, complicated ranking problem has been turned into a simple classification task. Just tell the positive examples apart from the negative ones. And that gets us to the ultimate goal. The machine learning model itself isn't really ranking things in the way we think about it. Its entire job is just to learn the mathematical line that does the best job of separating the good choice pairs from the bad choice pairs. That line is the ranking function. All right, so we've trained a model that understands these deep patterns of relevance. Now what? How does this actually get put to work inside a real, live search engine that you and I use every day? Well, the output of all that training is basically a set of weights. This list of numbers tells the search engine exactly how important each of those features is. For instance, the model might learn that a strong match in the title, that BM25 score we talked about, is the most important signal, followed by a match in the overview, and then maybe the document's release year is a little less important. But of course, in the real world, it's always a balancing act. This kind of super smart ranking can take a lot of computer power, which means it can be slow. So a lot of the time, a search engine will do a really fast, simple keyword search first to get maybe the top 500 results. And then it applies the smarter, more expensive LTR model to re-rank just that smaller set. It's a classic trade-off between speed and smarts. So let's just pull all of that together really quick. The big problem is that there's an infinite number of unique search queries out there. The solution is learning to rank, which finds general patterns of what's good instead of trying to memorize specific answers. The key insight is that clever pairwise trick, turning a hard ranking task into a simple comparison. And the result? A powerful model that can accurately rank results for searches it has never, ever seen before. And that really leaves us with a pretty fascinating final thought. Since these systems are ultimately learning from our collective behavior, our clicks, our choices, the quality of search is, in a way, a reflection of what we, the users, signal is important. It really makes you stop and wonder, what exactly are we teaching them?